AutoRemesher NOW.
Greetings and welcome. Today we stand at a fascinating intersection in the world of 3D. With the rise of AI-generated models, like this stylized head from Tencent's Hunyan, and the prevalence of raw 3D scans, we often find ourselves inheriting a chaotic legacy, dense, unstructured triangular meshes. They capture the form beautifully, yet they're structurally hostile to production. We need to bring order to this chaos. This is where AutoRemesher NOW enters the stage. It is not merely a retopology tool. Think of it as a translator that converts the raw language of scanned data into the structured dialect of production topology. We are starting with this AI-generated head, a dense soup of triangles. Our goal? To transmute this into a clean, animation-ready quad mesh. We begin with the primary operation, tris to quads. Now, pay close attention to the parameters, for here lies a common misunderstanding. You see this target triangle count? Do not be deceived by the name. It is not a literal order for the output quantity. Rather, think of this value as the sampling resolution, much like the megapixels of a camera sensor. It dictates the density of the voxel field the algorithm uses to understand the shape. A higher number captures finer curvature but yields a denser mesh. Here is the golden rule of this tool. The actual output in quads will typically be about 25 to 30% of this target number. So, if we desire a lightweight mesh of roughly 5,000 quads, we must set our target to approximately 20,000. It is a relationship of density, not a direct transaction. We generally recommend sticking to Mechanism 1, the default CLI approach, as it offers the most robust stability for this operation type. Let's adjust our settings. Notice how we are being conservative? In topology, modesty is often a virtue. We don't need millions of polygons when thousands will do the job elegantly. We also have edge scaling. This multiplier adjusts the inferred edge length. A value of 2.0 creates coarser, larger quads, which are excellent for speed. A lower value, such as 0.5, forces the algorithm to weave a tighter, more intricate net. For this head, we select the hard surface model type, which allows the topology to protect sharp creases more aggressively than the organic model type, which flows smoothly over curves. While we fine-tune this, consider why this matters. A raw mesh is just surface data. A remeshed object is editable geometry. By setting the target to 150,000 here, we aren't asking for 150,000 faces. We are asking for a level of detail capable of sustaining that density. The algorithm calculates the surface area, derives an ideal triangle size based on perfect equilateral triangles, and then optimizes. It prioritizes the quality of the flow over the specific count of the faces. Let's proceed. We check Auto Cleanup to remove any degenerate geometry that might confuse the solver, and we hit Remesh. The process is swift, and here is our result. Look at the wireframe. The chaos of random triangulation has been replaced by a structured flow of quads. It preserves the volume, the silhouette, and the intent of the original, but now it breathes. It is ready for subdivision, sculpting, or rigging. We always recommend that for this operation type called tris to quads, you choose a mesh that is between 100,000 and 500,000 faces. For larger meshes, we cannot guarantee reasonable processing times and success for this operation type. In any case, try to balance between the target triangle count and the original number of faces in the mesh to obtain smaller results. Once you have the result, if you need a denser mesh, you could apply a subdivision surface modifier to create more quads. However, if this add-on's operation type takes longer than normal, more than 5 minutes to process the mesh, or fails immediately during processing, I recommend that you follow the troubleshooting workflow provided in the documentation. Repair the mesh and run it through the tris to tris operation type to reduce the chances of bad geometry or topology, causing the tris to quads operation type to fail. Now, let us tackle a different challenge. This seashell. It is a dense scan, beautiful but structurally heavy. Here, we demonstrate the tris to tris operation. Why convert triangles to triangles? Because not all triangles are created equal. We want a uniform distribution. Here, we explore anisotropy. If we set shape adaptation to 0, we get uniform equilateral triangles, isotropic. But if we set it to 1, as we do here, the triangles become smart. They stretch and align themselves to follow the natural curvature of the shell's ridges. They flow like water over the surface, optimizing the mesh for simulation or engines that prefer triangulation. The two important parameters in the tris-to-tris operation type are shape adaptation and target points. We have already explained shape adaptation, but not target points. Basically, this parameter indicates the number of final vertices in the mesh resulting from the process, so if we set 30,000 points, we will obtain approximately 60,000 triangles. The other parameters can be left as they are, as changing them may affect processing time. But perhaps we simply need to distill the essence of the object and reduce its weight. We switch our operation to decimate. Unlike the standard Blender modifier, this algorithm uses a binning process to simplify the mesh while rigorously holding onto the shape. The bins parameter controls the resolution of this simplification. The higher the value of bins, the more detail will be preserved in the mesh. The lower the value, the more aggressive the decimation process will be. In this example, we will choose to leave it at the default value. We execute the decimation next. Instantaneous! We have dropped from hundreds of thousands of faces to a mere fraction without losing the visual integrity of the shell. This is ideal for LOD's levels of detail. Finally, we must address the health of our geometry. Scans and decimation processes can often leave a mesh non-manifold, with holes, loose vertices, or impossible geometry that mathematics despises. Several methodologies exist for mesh repair, among which the manual approach using Blender's native toolset proves particularly effective. This workflow involves entering edit mode to directly manipulate the geometry, identifying problematic non-manifold elements such as disconnected vertices, open edges, or internal faces, then systematically resolving them. Depending on the specific topology issue, this typically entails either using merge by distance to consolidate proximal vertices and eliminate gaps, or applying collapse operations to remove redundant geometry and restore surface continuity. But there is another option in the add-on. This brings us to the repair operation type. It acts as a digital healer. It merges vertices that are dangerously close, defined by the epsilon value, fills tiny holes, and resolves intersections. It is the necessary final step to ensure your asset is watertight and technically sound. From an AI-generated head to a raw scan, AutoRemesher NOW turns the technical burden of topology into a simple creative choice. Thank you for watching. If you are ready to claim mastery over your mesh data, there is no more opportune moment than the present. We invite you to Superhive Market, where, until December 3rd, we are celebrating Cyber Sale Week with our deepest discounts. However, for those who seek to turn their workflow into a true powerhouse, consider the ultimate alliance, the AutoRemesher NOW and Mutamesh bundle. By uniting this tool with Mutamesh's 4 additional remeshing engines, you secure a comprehensive topological arsenal. Instant meshes, Quad Wild, CWF, Adaptropic, and our Tris to Quads, Tris to Tris, and Decimate. For this week only, we offer a compounding harmony of savings, the standard 42% bundle discount, further deepened by an additional 25% reduction. Do not let this geometry, or this opportunity, go to waste.
AutoRemesher NOW.